So we've discussed one of the colligative properties called Raoult's law, which is about vapor pressure lowering. Now we're going to look at another colligative property referred to as a boiling point elevation. And so boiling point elevation simply means that a solution that contains a solute and a solvent boils at a higher temperature than just the pure solvent. So if you were to add a solute to water, you would increase its boiling point because now it takes more energy to break those intermolecular forces. So since it takes more energy, it takes a higher temperature. And so if we look at the phase diagram over here, the one in the solid is the regular phase diagram of the pure solvent. When you add a solute, the dashed line is the adjusted phase diagram of the solvent. So you can see when the solvent is in solution, the freezing point decreases and the boiling point increases. Because again, this happens because once you add a solute, you're replacing, for example, if we add sodium chloride to water, we're replacing the hydrogen bonding with ion dipole. So therefore, it takes more energy for the molecules of water to leave the surface of the liquid or the surface of the liquid to become vapor. And therefore, since it takes more energy, it elevates the boiling point. And so how much it elevates the boiling point is proportional to the molality of a solution. So if you know the molality, you can calculate how much the boiling point will increase. And so the equation for that is the change in the boiling point is equal to a constant times the molality. And you can look down here, and for different solvents, it has different constants, which are called the boiling point elevation constant, KB. And every solvent has a different KB associated with it. Now, you're not expected to know these constants. They would provide it for you. In addition to that, it shows you the different boiling points of the solvents. So if the solvent is not water, the boiling point will be given to you. However, if the solvent is water, then it's understood that people know what the boiling point of water is in degrees Celsius. So you would use the KB and the molality of your solution to calculate how much the boiling point would increase. Now this is just the change, delta TB. Delta TB then equals the boiling point of solution minus the boiling point of solvent. So to find the boiling point of solution, we would need to move the boiling point of the solvent over here. So when you get to this point here, don't stop. That's not the answer. You have to add it to the boiling point of the pure solvent to get the boiling point of the solution. And so on our next few examples, we're going to look at some calculations involving boiling point elevation. So here we have a 23% mass solution of aspirin and carbon tetrachloride. What's the boiling point of this solution? So it gives us the molar mass of carbon tet. It gives us the boiling point and the KB of carbon tetrachloride, the molar mass of aspirin, and it says it's a 23% mass solution. So again, to calculate the boiling point of a solution, delta TB equals KB times the molality. And then we know that the boiling point of the solution equals the boiling point of solvent plus delta TB. So it gives us the boiling point of the solvent which is 76.8 degrees Celsius. And it gives us the KB, Again, the KB comes from a chart, 5.02 degrees Celsius per mole. So in order to determine the boiling point of the solution, we need to know the boiling point of the pure solvent, which we have, so we can check that off. And we need to know the delta, the change in the boiling point, which we don't know. That's our question mark. So to find the change in the boiling points, we need to know the KB and the molality. Well, the KB we have, the molality we don't have. But what we do know is it's a 23% mass solution of aspirin. So now we have to convert mass percent into molality. So we assume 100 grams of solution. If we assume 100 grams of solution, we know the grams of solute. And we know the grams of solvent. Remember, molality is moles of solute over kilograms of solvent. So we're going to convert this solvent to kilograms. And now from the mass of solute, we're going to find the moles of solute. So moles is 0.1266. So now we have the moles of solute, we have the kilograms of solvent, we can find molality. We get 1.66 molar solution. So now we have the molality. We can plug it into delta TB equation and solve for delta TB. And again, this is just a change in the boiling point. It's not the boiling point of the solution. And we get 8.33 degrees Celsius. So that's the change in the boiling point. Now to find the boiling point of the solution, we just add that to the boiling point of the pure salt. And we get, 85.1 degrees Celsius. So that's how much the boiling point elevated. It elevated up to 85.1 degrees Celsius. So here we have a sugar. Fructose contains 40% carbon, 67% hydrogen, and 53.3% oxygen by mass. A solution of 11.7 grams of fructose and 325 grams of ethanol has a boiling point of 78.59 degrees Celsius. It tells us the boiling point of ethanol is 78.35 degrees Celsius and the KB is 1.2 for ethanol. What's the molecular formula of fructose? So now, to find the molecular formula, this is a kind of a refresher from Gen Chem 1. So molecular formula equals some number times the empirical formula. And so the way we get this n is equal to the ratio of the molar mass of molecular formula over the molar mass of empirical So the way we find the molar mass of the molecular formula is by using the information given to us about the boiling point elevation. The way we find the molar mass, should be molar mass, of empirical formula is by using the percents of each element in the compound. And there are different ways to approach this. This is just the way I'm going to approach it. So the first thing I'm going to do is to determine the empirical formula. So to do that, I assume 100-gram sample. And from that, I can get the mass of each element. So I get 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. Now we're going to divide by the molar masses to get the moles. And so here you'll notice that carbon and oxygen are roughly the same. So we can divide by the moles of oxygen. It's approximately 1 for carbon. It's approximately 2 for hydrogen, and approximately 1 for oxygen. So our empirical formula is CH2. Oh, this is the empirical formula. So the molar mass of this is 30. We have the molar mass of the empirical formula. Now we need to get the molar mass of the molecular formula. We divided by 3.331 because that's the smallest number of moles from the 3 different elements. So you always divide by the smallest number of moles to get the ratio. So now we need to use the other information to calculate the molar mass of the molecular formula. And just to kind of recap, we know that moles equals mass divided by molar mass. So to rearrange this to find molar mass, it equals mass divided by moles. So if we know the mass of the solute and the moles of the solute, we can calculate the molar mass of this fructose. And so we know the mass of solute is given to us 11.7 grams. The moles of solute, we don't know. So in order to solve this problem, we need to know the moles of solute. So we have to use the other information. We know it's 325 grams of ethanol. We know the boiling point of the solution. We know the boiling point of the pure solvent and the Kb. So we know if we solve for molality equals moles over kilograms of solvent. So moles equals molality times kilograms of salt. So in order to solve for the moles of solute, we need to know the molality and the kilograms of solvent. Kilograms of solvent we know 0.325 kilograms is given to us in the problem. But the molality we don't know. So now in order to solve for the molar mass of the molecular formula, we need the moles of solute. In order to get the moles of solute, we need to know the molality of the solution. And that brings us to delta TB equals KB times molality. So in order to solve for molality, it's delta TB divided by KB. So do we know the KB? Yes. KB is given to us 1.2. Do we know delta TB? No, but we do know the boiling point of the solution is 78.59, and we know the boiling point of the pure solvent is 78.35. So now we can determine delta TB. And we get 0.24 degrees Celsius. So now that we know delta TB, we can calculate the molality. So molality equals 0.24 divided by 1.2. And we get 0.2. So the molality of this solution is 0.2. So now we know the molality is 0.2. We know the kilograms of solvent. We can find the moles. So moles equal 0.2 times 0.325. Get 0.065 moles. So now we know the moles of solutes. We can determine the molar mass of this solute. So we know the mass of solute, the moles of solute. Molar mass is just mass divided by moles. And we get 180 grams per mole. Now this is the molar mass of the molecular formula, and we have the molar mass of the empirical formula. So now we can calculate N. N is equal to 180 divided by 30, which equals 6. So to find the molecular formula, we take 6 times CH2. So we get C6H12O6. And that is the molecular formula of this fructose. So again, just to recap, we had to use the information in the first sentence to calculate the empirical formula, because in order to calculate the molecular formula, we need to multiply the empirical formula by some N, which is some number. The way we find N is the molar mass of the molecular formula over the molar mass of the empirical formula. So once we found the empirical formula, we can find its molar mass, so that's checked. Now the rest of the information is used to determine the molar mass of the molecular formula. So molar mass is mass divided by N. So it gave us the mass of solute, but not the moles of solute. So in order to find moles, we have to look at molality. So moles equals molality times kilogram of solvent. So in the problem, it gave us the mass of solvent. We converted that to kilograms, but it did not give us the molality. So then using the boiling point information and the KB, we could determine the molality. And once we had that, we can find moles, and then the molar mass of the molecular formula, and then the ratio 6. And so that's how boiling point elevation is used. Is typically as a way to find molar mass of compounds, which is probably something that you'll do in a Gen Chem 2 lab. Usually you have an experiment where you determine the molar mass based on boiling point or even freezing point depression. So on that note, that's all for this lecture. Until next time, we'll see you later.